Hey, geometry friends, here we are looking at chapter 5, and we're going to do 5-1 bisectors of triangle. So, we've got some new vocabulary today, and the vocabulary is perpendicular bisector, and it's exactly what it sounds like, right? So, if you're walking down the street and you see this segment, some segment AB, and a red line claims to be AB's perpendicular bisector. Here's the things that have to happen. Some line, let's call this line M. Line M claims to be the perpendicular bisector of AB, of segment AB. The things that would have to happen in order for that to be true would be that it would have to bisect AB, meaning cut it in half, meet it directly at the center, and it would have to be perpendicular to AB. So that's what we have, a perpendicular bisector, and there we go. That's one word that we have done. The next concept we need to talk about is concurrent lines. Basically, if you have three or more lines that meet in a particular point, these lines are considered concurrent lines. Right? Not that big a deal. So if you got three lines that meet in a point, they're called concurrent lines. And similarly, you probably would realize that the point of concurrency is simply that guy right there, the point in which they all meet. The point in which they all meet. Now, this idea of circumcenter deals specifically with a triangle. So given this triangle, right, we have three sides: side AB, side BC, and side CA. These three sides can each have a perpendicular bisector. So it will bisect the segment of the side, and let me do that. Let's make this nice and purple. Bisect the center, be perpendicular, and bisect the center of each side. It continues on like that. And this side will have a perpendicular bisector, and it continues on like that. And this side will have a perpendicular bisector, and it continues on like that. So the point where these three meet, these three perpendicular bisectors meet, is a point of concurrency, because obviously we've got concurrent lines where three lines intersect at one point. It's called the point of concurrency, but the point of concurrency of the perpendicular bisectors of a triangle would be the circumcenter. Okay, so if we take each side and we find the perpendicular bisector of each side and we draw it, they meet in a point, and that point is called the circumcenter of the triangle. Now for this other one, the end center, we take another triangle. Let's say triangle ABC again, and what we'll do is we will bisect each angle. So these are angle bisectors. So we're going to cut each angle in half. And the angle bisectors, it's going to cut each angle in half, right? Hence the definition of the word bisector, right? Cut it in equal halves. So if we take all three angle bisectors, lines that continue on and on, or raise, the point where these three end up will be at the end center. So this is called the end center. So this is when we take the angle bisectors, they are concurrent lines, meaning they all meet in a point. The point of concurrency, that point of meeting, is called the end center when it is created by the angle bisectors of a triangle. So that's our end center. And that's our vocabulary for today. I do have one concept that I think we talked about, but comes up again in one of the problems. So I'm going to remind us that when we have a right triangle, we can talk about the sides as being A and B, and the hypotenuse, the longest side, is being C. And the Pythagorean Theorem reminds us that anytime you have a right triangle, the way these sides relate is that you take the side A, the length of the side A, and you square it. You could add to that B squared, and that's going to equal C squared. That is the relationship between any of the sides of a right triangle. So for instance, if this side were length 3 and this side were length 5, and I didn't know this side, I could use this formula to solve. And so what I do is I put 3 squared there. I'd leave my b squared as it is because that's what I'm looking for. And then I'm going to put 5 squared here. I work the problem by squaring the numbers that I can square. And now I'm going to solve for b by subtracting 9 on both sides, getting that b squared is equal to 16. And b, because we're dealing with a positive real number thing, not going to do plus or minus 4, I'll just do is equal to 4. That's all we need right now. And so this is true whenever you have a right triangle. We actually have been dealing with this concept when we deal with the distance formula. The distance formula is really just a variation on the Pythagorean Theorem, which this is. So in case we need it, we have a little bit of reminder. This is the Pythagorean Theorem. Okay. So here are some theorems that we have that are going to be helpful for us. So theorem 5.1, perpendicular bisector theorem, it basically says this. If a point is on the perpendicular bisector of a segment, so we're starting off with segment AB, and we have the perpendicular bisector, let's call it CD. C is some point on this line, CD, right? Then this point, this is what this is telling us, then this point is equidistant from the endpoint. So it's written like this. If CD is a perpendicular bisector of AB, then AC is equal to BC. Then we know from that these guys are equivalent to one another. So given a perpendicular bisector, any point on that line will be equidistant, this line continues on, from the endpoints. Okay? That's what this theorem gives us. And let's take out this next theorem. This next one is the converse. So it's kind of going in the opposite direction. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So if I say, hey, here's this point E, and it's equidistant from B and from A, right? Some point E is equidistant from the endpoints of a certain segment, then I know for a fact that that point must lie on the perpendicular bisector. All right, read it over if it's not feeling too good, but they really do relate to one another very well. They're kind of coupled together. So with all this information, let's go ahead and get started and try to work on this problem. So find each measure. So we're given that we're given some information. We're given that CA is a perpendicular bisector, right? Because it's perpendicular to DB, and it shows that it's perpendicular by this little rectangle, and it bisects by these two equivalent segments that it makes BD broken into BC and CD. And then we're asked to figure out what AB is. Well, we know that any point from our theorem above, any point on the perpendicular bisector will be equidistant from the endpoints. Therefore, this has to be equal to this. Therefore, AB has to equal 4.1. Let's check out this next figure, WY. WY is this little segment here. But looking at this, we see that this is perpendicular. We see that these two segments are equivalent. So we know that X must lie on the perpendicular bisector, right? Because if you have a point, how did it go? If you have a point that is equidistant from the sides of a segment, of the two endpoints of a segment, you know that it lies on the perpendicular bisector. Since this line is perpendicular, it must be the perpendicular bisector, and therefore this little segment here is going to be 3. It's going to be equal to this guy, right? And now we have this one, which says that RT is what we're looking for. We see we have the same setup. You can assume already, now you're like professionals at this, you're like, clearly QR is equal to TR. Therefore, if I can just figure out what that is, and of course, our textbook likes us to have strong algebra muscles, so we get a little algebra problem to play with. We're going to get rid of the 2x's on both sides. We end up with 2x minus 7 is equal to 3. Move this 7 over here, it becomes positive, whoosh, right? Then we get a positive 10 is equal to 2x. And then we divide both sides by 2. And voila, x is equal to 5. All right? And I just almost got played myself, because usually I'll be like, yeah, 5 done. But we got to figure out what they asked for. They didn't ask us what x is. They asked us about RT. RT can be figured out by knowing that the fact that RT is equal to 4x minus 7. Therefore, 4 times 5 minus 7, which is 20 minus 7, is going to give us 13. The true answer is 13. My bad. All right. All right, so another theorem, the circumcenter. So circumcenter theorem tells us this. So remember, the circumcenter is where the joining of all of the perpendicular bisectors within a triangle. The perpendicular bisectors of a triangle intersect in a point called the circumcenter. That is equidistant from the vertices of the triangle. So now the circumcenter, if you find the circumcenter, you know that the distance here, let me see if I can do this. Let me highlight it, maybe that might be better. This green line, highlight is better, right? This highlighted line, and this highlighted line, and this highlighted line are all equivalent. They are now equal in distance. This point in the circumcenter is equidistant from the endpoints, and that's what this theorem gives us. So that's pretty cool. All right, so here's another real-world example. A stove, and we're not going to do this one. We're just going to observe and talk. Okay, so a stove S and a sink K and a refrigerator R are positioned in a kitchen as shown. Find the location in the center of an island workstation so that it has the same distance from the 3 points. So what you would do, and it's going to explain it here, but I'm going to talk to you about it anyway. So here are these guys. We want to find some point in the middle that's going to be equal in distance, remember? And how did we get that point? If you go back up to the theorem that we just talked about, that theorem of equidistance is found by finding the perpendicular bisector. So if you had to do this, you would literally find the bisector. We could construct it. We could find the bisector of each of these sides. Let's use a pen. We could find the bisector of each of the sides and draw the perpendicular bisector through it, and then they would all meet in the point that we're looking for, and that would be the perfect distance where I guess if a person standing in this kitchen will be equal in distance to each of their appliances. Okay, so with that in mind, we're going to talk about a concept called angle bisector, or the angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the side of the angles. So let's kind of analyze a little bit. So here is the angle bisector, BF, and F is a point on the angle bisector. So the angle we're talking about is this one, DBE. So DBE, we use 3 letters to talk about this angle, or I can call it angle B, since there's not, well, I'm going to not do that. I'm going to call it angle DBE, so you're sure that I'm talking about this angle here. All this here, right? This BF is a bisector, is an angle bisector, so it's going to cut this angle in half. When this angle is cut in half, you're going to observe that F is on that angle bisector, and therefore, this theorem says if you have a point on the angle bisector, then we know that that point is equal in distance from the sides of the angle. So any point here will be equal in distance from the sides. Any old point. That's what they're telling us. Okay. The converse of this is if you have a point, if a point is in the interior of an angle and it's equidistant from the sides of the angle, then we know that that point lives on the angle bisector. Then it is on the bisector of the angle. So if I told you, hey, here's some point F and it is hanging out here on some line, but point F is equidistant from D and F, then what I know is that, oh, then the segment BF must be the angle bisector. So it's kind of like the same coupled theorems we did before. Let's take the rest up in the next video.